Variance is what we want to look at today. That's the next statistical measure we're going to talk about. So x is our discrete random variable. Variance is defined this way: the sum of x minus mu squared times px. Px, you recall, is the probability that our random variable is equal to whichever outcome we're talking about. Mu, or mean, we saw as expected value. We now know how to work that one out. Alright, this is where I was up to, wasn't it? Yeah. So this x minus the mu is what we call the deviation. How far the result deviates from the actual average. And the reason we square it is we want to ensure it's a positive number. Because some would be below, some would be above, and if we're going to sum them up, we don't want the negatives to take away from the positives. It won't give us an actual answer. So that's why we square it. It's a measure of spread. How far out the data is spread. Well, you look at the same example that we did yesterday, our milk survey. We want to find the variance of this data. So we drew up our table yesterday, you recall. We came up with that. We ended up finding that the expected value, or the average, was 2.2. So that's where we got to yesterday. So how do we now change this table to get more information? Well, now I need to know what x minus the average is squared. So for each one of those, I'm going to go x minus 2.2 and then square it. And there's my answers down below. I actually want to know that number times px. So now I multiply that one with px, and then that's the row I sum, and I get 1.52. So the variance is 1.52. So that's the actual formula. But if I manipulate this formula, I can come up with an easier way of doing it. So we're going to do it this way. So there's our formula. So I'm now going to manipulate this. That essentially is the expected value of the random variable x minus the average squared. Because remember, our definition for expected value was the sum of, then the thing we were investigating, times the probability of x. And that's what we've got here. But then yesterday we saw some rules that allows us to manipulate expected values. So if I expand out x minus mu squared, I'm now finding the expected value of this. X squared minus 2 mu x plus mu squared. But we had a rule that said we can separate each individual bit out. So I can say, well, it's the expected value of x squared. But then what I've also done is said, well, hang on, the average is just a constant. It's the same for the whole set of data. So I can factorise that outside of the expected value of x. And then the expected value of a constant, well, is going to be the constant. So the expected value of mu squared will be mu squared. Okay? That's what we will get every time. But now I can take that a step further, because of course the expected value of x is mu. And so this middle term becomes minus 2 mu squared. So there is a new formula. We can say it's the expected value of x squared minus the average squared. That now means our table becomes far more logical. So remember, expected value of x squared will become x squared times the probability of x. Okay. So when I set up my table, that is where we got to yesterday. We had these rows, px and xpx. 2.2 ends up being the expected value of x. So that's mu. But now all I need is one more row, and it's a heck of a lot easier, because all I now need to do is x squared px. So I now just multiply the row xpx by x. So 0 times 0, 5 on 25 times 1, and so on. So it's just building a structure. I go px, then I go x times px, then I go x squared times px. It's a much more logical thing and easier to remember. Okay, so we plug it into our new formula. Right? So there's our expected value of x squared. So the variance we're now saying is the expected value of x squared minus the average squared, and we've got both of those pieces of information. And surprise, surprise, we end up with the same number, 1.52. So to me, that's a lot easier than the other way. And a lot easier to remember as well. Now, you might not have heard of variation before. You heard of this thing, probably standard deviation. And I don't know if you remember the formula for standard deviation, but it's quite an involved formula. But it now becomes very easy, because we've just worked out variance. You see, variance because we squared it, the units of whatever we're measuring are now squared. So if it was the length of something, it would be centimetres squared. But the data we're in is just in singular units, so just centimetres, for instance. So how do we get these units squared back to units? Well, we take the square root. So the standard deviation is simply the square root of the variance. So once I've worked out the variance, find the square root, there's my standard deviation. And then that tells us about the spread of the data. That's why we often use, for variance, the symbol sigma squared. Because little sigma is the symbol we use for standard deviation. And variance is that squared. So sigma squared you'll see representing variance. Okay, so in our example, it would be the square root of 1.52, which is, well, it's 2 decimal places. It's 1.23 would be the standard deviation of our data, the spread. So that on average, for want of a better word, is how far away a piece of data is from the average, about 1.23. That brings up this idea of standardising the data so you can go and compare things. People often do it because you want to compare. What was my test result here compared to my test result here? Which one did I do better? And of course tests are of different levels of difficulty, so it's not always a fair comparison. So it's just one measure we can use. Alright, do not panic. You do not have to know where this comes from, but I want to show you where it comes from. And this is what people do. The non-mathematical people who think they know what they're doing but they don't understand maths, i.e. English teachers. No, I didn't say that. Alright, so the original data has a certain average and a certain variance. But we want to change it so we can compare things. And what sometimes happens is they say, oh, look, we're not happy with the average. So what we're going to do is we're just going to add 5 marks for everybody. I don't know if you've ever seen teachers do that. So everyone's score goes up by 5 marks. Is this a fair thing? But this is what happens when you do that, okay? So my new random variable y will be the old random variable plus this constant amount. So what's my expected value now going to be? Well, it would be the expected value of x plus c, which I can break up into 2 things. But the expected value of x is the old average, and expected value of a constant will be the constant. So all I've really done is I've added that to the average. Well, that's what they were trying to do. They wanted to lift the average. Okay, they've achieved that. But what happens to the spread of the marks? So I now want to find the variance of x plus c. Well, the variance is defined to be the expected value of it minus the average, so this will become the new one. I'll expand out the x plus c, or squared, and playing around with that I can eventually come down to this. And you'll notice it's exactly the same as what it was. The expected value of x squared minus the average squared, which we said was the variance of the original data. So if I was to see it on a graph, if that was the original data, if we plotted all of it, all we've really done is shifted that graph horizontally. So that's the effect of adding a constant amount. Not a great way to standardise data, to be honest. I don't know that anyone does this, but then maybe they go, oh, well, all right then, maybe we'll just multiply or divide every mark by a certain amount. Well, what would happen there? So I'm now defining this random variable z to be x divided by a constant amount. So what would happen to the expected value? Well, it's going to be the expected value of x divided by a constant. Expected value of a constant, well, constants I can factorise out. So it would be the same, I'd end up with the average divided by k. Makes sense. If I'm dividing every piece of data by a constant amount, you'd expect the average to be divided by that constant amount as well. What happens to the spread? Okay, split that up into the formula. Again, well, the constant I can factorise out. So it's the expected value of x squared over k squared minus the average squared over k squared. That I can write as one fraction. Then playing around with the top. Well, the top is the variance. So I get the square root. I've ended up squaring the variance. Now, depending on whether that number is bigger than 1 or less than 1, whether that becomes a bigger spread or a smaller spread. But basically, there's the original data. What has happened? The new data, well, yeah, it's shifted. I've assumed k is bigger than 1, so when you divide by a bigger number, it'll become smaller, so the average is moved to the left, and the data comes in. It gets a bit tighter. I don't know if anyone ever does it that way. That'd be crazy. But that's not what we tend to do. You don't have to worry about how I got all that. I just want to show you this is how it happens. We tend to use things called Z-scores. Again, let me show you what happens with a Z-score. So we try to what we call normalize the data. So we get all the data so that every piece of data has the same average and the same spread. And if that's true, then I can compare these two sets of data. Basically, that's the formula. To get a Z-score, you get the original score, you subtract the average, and you divide it by the deviation. So what happens to the expected value when we do this? Okay, we have the expected value of x minus mu on the deviation. But the deviation is a constant number for the data, so I can factorise that out. I now want the expected value of x minus the average, which will be, again, I could split that into two things. I've done it all in one step there. I could split it up into two things. The expected value of x is the average, minus the expected value of the average, it's a constant amount, would be the average. I end up with 0, and becomes a really beautiful point to use for the centre of the data, because it's right in the middle. It's at 0. So we change everything so it has an average of 0. The deviation when I do this, okay, so I now want to find the variance. So the variance, again, the constant is sigma squared, variance of x minus mu. I end up with sigma squared on sigma squared, which is 1. So the spread is always 1. So we're playing with really nice, neat numbers. So when you convert to a Z-score, everything's average of 0, deviation of 1. So when you look at a Z-score, you're simply saying, well, how many deviations am I away from the average? That's what it's essentially saying. I don't know there's any standardised data in the actual exercise itself, so it was interesting to show you where it comes from. We will look at it in later topics. It certainly comes into play later.